Now we're going to talk about magnetism. So, what is magnetism? Well, magnetism is another force. It's another force of attraction or repulsion of magnetic material because of a specific arrangement of its atoms, um, specifically the electrons. So, the ends of a magnet are where the magnetic effect is the strongest. We call the ends of the magnet the poles. Every magnet has two poles, a north and a south. You can see them clearly marked on this illustration. So, like charges repel like charges. You can see the force repelling from north to north, and opposites attract. You can see the forces here connecting. They're attracted to each other. The law of magnets. Okay, we show this with what we call flux lines. You can see the magnetic flux lines showing the attraction between the north and south. And you can see the flux lines showing the repulsion from north to north. You can see clearly there is no force, there's no flux lines in this area because they've been pushed apart. Once again, we call these magnetic flux lines. We can also call these field diagrams. Once again, poles always come in pairs, north and south. So if you were to cut that magnet in half, you would still get two magnets, each still with a north and south pole. And we will very soon see why that is. But if you cut it in half, two magnets, each still having a north and south pole. Magnetic fields, right? I was just referring to the magnetic field lines that we see. Flux lines, magnetic field lines, you can see them all, okay? And that field is once again that area where the magnetic forces can act. Very similar to electric fields. So, if you look at a regular object, the atoms they arrange themselves. They're kind of in groups, and when something becomes magnetic, then all their groups are basically going in the same direction, right? So we're talking about domains, these areas of atoms that have grouped each other. And when they all go the same direction, then we're going to have something that is magnetic. So here you see all these domains all going in multiple directions. And here you see all those domains, everything's going in the same direction. So when everything lines up, then you get something that is magnetized. It's magnetic. Everything's aligned. All those particles, they're aligned basically in the same direction. And here you can see why, if we were to cut this in half, you would get two magnets with you still have two poles, because if you look at these arrows, you got, one end and the other end. If you cut this right down the middle, then you still have arrows all going the same direction. So if everything back here would be maybe your south pole, everything up here would be your north pole. You cut it in half, and then you would still have all the arrows facing the same direction, so you still have a north and a south pole. That's why you get two magnets if you cut one magnet in half, still with north and south poles. So this might be what the substance, something that's unmagnetized, might look like, and then when you magnetize it, you clearly have everything lined up all nicely and orderly, causing it to be magnetized with your north and your south poles. So, how to break a magnet, which we do not want to do. Obviously, if you drop a magnet, it would not be magnetic anymore, because you would take all those domains and you would kind of jumble them around, so they would be random again, not arranged specifically. Thereby, you're not going to have that magnetic force. And if you heat a magnet, we know what happens when substances get warm. All their atoms move around much more quickly, and it's going to mess up the arrangement of our domains if all those atoms are moving around rapidly. Now the Earth, as you can see here, the Earth is a giant magnet, right? Our magnetic field from the Earth's magnet extends out in what we call the magnetosphere. So that's how far it extends out, the magnetosphere. You can see it here, very similar field lines, flux lines. You can see those here. Right. Now, something we call the solar wind is a flow of magnetic particles from the sun, right? And when that hits the Earth's magnetic field, then something strange happens. It glows. That's right. Where those particles hit the strong Earth's magnetic field up in the poles here, then you get the aurora borealis in the northern hemisphere, the northern lights, that kind of glow. And if you're in the southern hemisphere, then you see the aurora australis, which is the same glow, just in the southern hemisphere. And that is caused by the sun's magnetically charged particles coming into contact with Earth's magnetic field, especially at its very strongest points, causing these lights. We use Earth's magnetic field all the time to navigate. Not as much anymore because we have GPS, but back in the day, right, with our compasses, because a compass is essentially a magnet, and so it's going to be drawn to the strong north or south pole of the Earth's magnet, causing it to always point in that specific direction. So you can use it to tell where you're going. Electromagnets. Now we're combining electricity and magnetism. Electromagnets are formed by kind of wrapping a wire around a metal, specific metals, running a current through that wire, and then it turns that metal into a magnet. Okay, this being a very large electromagnet here used to pick up scrap metal. It's very interesting. So, the source of electromagnetism is an electric current, right? It's flowing through this wire here, and it's going to create a magnetic field as it flows through this wire when it's wrapped around, especially an iron bar. There are some other metals this works for mostly, but it works very well with iron. That electric current is going to line up the domains in the iron while the current's flowing, causing it to be magnetic. So you have to have electric current flowing through there, and it does cause it to be magnetic. So here, right, you see these paper clips kind of just hanging out there. You've got this wire wrapped around this bolt here made of iron, and there's no electricity, so the paper clips are kind of just hanging out there. But then when we do apply that current to the wire, sending it through there, you can see the attraction, the magnetic attraction between the bolt and the paper clips. So no current, no magnet. Current, then you get a magnet. Very simple. So how are we going to make that electromagnet stronger? Well, we can increase the number of coils, right? You can wrap more wire around the piece of metal more times, causing obviously more of that current to be exposed to the metal. Or you can increase the amount of current. You can change the power of that current flowing through the coiled wire, causing it to make the electromagnet stronger. Now let's talk about electric motors. We use these all the time in our daily lives. So what's going on with an electric motor? How does it work? You can see here that this is a circular kind of magnet, right? You have that permanent magnet right there on the outside of your electric motor. And then on the inside you have an electromagnet. So you're going to have that piece of metal with the coiled wire around it. When you run the current through the electromagnet, right, it's going to be repelled and attracted to the poles of the permanent magnet, because here you have north pole, here you have a south pole. If you have that magnet in here, it's going to be repelled by one side, so it's going to get pushed around, and then it's going to be attracted and then it's going to be pulled. So you push and pull and push and pull, and it's causing this to turn, which is what makes our motor work. So when you have that electromagnet, you run that a little bit of a current through it, and it's going to cause this to continue round and round and round as it's repulsed by one side, and then as it turns around, it's going to be attracted to that side. So one pole is repelling while the other is attracting, causing it to continually spin. That's what makes an electric motor work. It's awesome. Your electric generator, which is it's going to be the opposite of a motor, right? We're generating current rather than using it to make something turn. So you have some sort of a conductor, right? It's going to be generally a wound up wire, and you turn it inside of a magnet, and when the wire is moving through that magnetic field created obviously by the magnet, we saw the magnetic fields before, as it moves through that magnetic field, it's going to cause the electrons to flow somewhat, and that is the definition of electric current. So the magnetic field is causing the motion of the electrons, that is causing electric current. So we are creating current in that generator by creating a motion of electrons through that magnetic field. So you can do this one of two ways. You can either rotate that coil inside of a large magnet, or you can rotate a magnet inside of a coil of wires. But either way, that magnetic field is causing the motion of those electrons, and it's going to be producing some alternating current for us. That's what a generator does. Alright, so when we generate power, like a power plant or something like that, we generate you've seen a power plant, we have this huge amount of electricity and current that is being created, and we can't send that huge amount into our homes because it will be way too much. So we have to use something we call a transformer that changes voltage into different voltage levels, because we can't have that force, that huge force of electricity coming into our houses, but it takes larger voltages to push that electricity from the power plant as far as it needs to go. You need that force to push it down. So a transformer is going to change the voltage of electricity, and it does this by having different sets of coils. So you might have one that's got a lot of coils and one that's got little coils, or vice versa, in order to change the power, the voltage of the current. And here's a nice picture of parts of a power plant. This is a transformer that is used at a power plant. Once again, so the factor that determines whether a transformer increases voltage, which we call a step up, or decreases voltage, which we call a step down, is the amount of coils, the turns in these coils. You have a primary coil and a secondary coil, and depending on the amount of turns, the amount of coils they have, that's going to tell you whether it's going to increase voltage or decrease voltage. And I know you might be a little confused, but here's a great picture that it's going to illustrate what's going on. This is a step down transformer. It starts off with high voltage, right? Lots of force pushing that current, and you go from a lot of coils to a little amount of coils, and it brings down the voltage. So we're going to get some more current. It's going to flow faster, but it's not going to flow with as much force. So we're going to be able to use it in our homes. So you go from many turns to a few turns, and that steps down the voltage. It decreases the voltage. And then here's another picture that's going to show you have fewer coils here, and you have larger amount of coils here. So that's what is going to, you have the primary voltage going in with a small amount of coils, and then you have the secondary voltage with a large amount of coils, and this would obviously be a step up transformer, which would be the opposite of what we just saw. So that is how transformers work, and we will definitely go more in depth with this very soon. So just remember, electric motor converts electrical energy into mechanical energy. Generator converts mechanical energy into electrical energy.